All right, hello and welcome to CSCI 26. I am excited to teach you this semester, and we are going to learn some cool stuff together. So, first of all, I am not making this presentation full screen because I get much cooler pens this way, among other things. I'll also be switching back and forth between the terminal and here and the web browser, so this is why it's a little bit smaller than it could be. Sorry, but I promise it's worth it. So, let's do that normal, boring first lecture stuff. Okay, so let me introduce myself. Let's go over the syllabus and try to stay awake. But we will, I promise, eventually get to interesting CSCI 26 concepts before the end of this lecture. Okay, so look forward to that. Let's all try to stay conscious for that. Okay, so yeah, let me talk about myself first. So hello everybody. My name is Lawton Nichols. I use he/him pronouns, and I will respond to whatever you'd like to call me. So you can call me Mr. Nichols, you can call me Dr. Nichols, or Professor Nichols, if I know how to spell. But honestly, I'd prefer it if you just dropped all those and call me by my first name. Please call me Lawton. I would like to earn your respect. I don't want your fake respect with these titles. All right? So a little bit about my background is that I went to Fresno State for my undergrad. I got a bachelor's in computer science there, so that's not too far away, right? And then I went to UCSB, UC Santa Barbara, for grad school. That's where I got my master's and my PhD. And I have dedicated my firstborn son to the cause of computer science. This is Lonzo, as a kitten. He's much older now. He's like 5, and he's bigger too. He is super cute, and I named him after Alonzo Church. He was a very famous computer scientist, and among other things, he was the PhD advisor to Alan Turing. So if you haven't heard of him, you'll definitely have heard of Alan, right? So yeah, that's a little bit about me. I like to do normal human things too. I like to dance, play guitar, stuff like that. So feel free to talk to me about those fun things in office hours. And then just thank you in advance, right, for putting up with me throughout this semester. It's going to be a fun one. I know that we live in a weird post-COVID era now, and nothing makes sense anymore. So we will get through it together, though, okay? So yeah, let's talk a little bit about the syllabus and just like the logistics of the class. So remember that you need to read that full syllabus to understand everything. I'm just going to give you the highlights, and I'm going to go very fast because this is boring for me too, all right? So you should still listen, though. Don't fast forward. All right, the first thing, logistics of the class, is that this is an asynchronous class. All right, so I'm going to do the following. I'm going to pre-record all the lectures and all the labs ahead of time. And here's kind of the schedule that I'll keep every week. So like you can expect for the first lecture video of the week up by Tuesday, and the second one up by the end of Thursday. All right, so consider this to be like a Tuesday, Thursday kind of class. And then I'll also, like any labs that I introduce during a certain week will be up by Friday afternoon. Let's keep that schedule. All right, so that's what I'll plan for. And you will find that I'm going to reuse a lot of older recordings that I've made in the past. They're still good, a lot of them. But please, please, please watch the videos on Canvas as I post them on Canvas. Please don't try to go to YouTube and watch the next lecture before it's posted, because I might be re-recording that one, and there might be new information that needs to be given to you. Okay, so just keep that in mind. Please don't try to get ahead. I'm doing this stuff in a certain order for a reason. All right, and yeah, as far as the timing for like important stuff goes, because I can't expect you to be anywhere, I'll give you a wide window to take stuff. So like for exams, for example, I'll give you at least a 24-hour window to take exams in this class, okay? They will be timed though when you start them, so it's like an hour and 15 minutes or an hour and a half for like a midterm, something like that, and longer for a final. So that's what you can expect. And while we're on that topic of expectations, let's talk about just like the complexity of the class. So I would say that CSCI 41, the prerequisite to CSCI 26, is the hardest class we have here at Clovis, okay? Which is great for you, right? This is technically an easier class then. But honestly, I can't say that this one's easy too. It's just not as hard, I would say. So this is a math class, first of all. If you didn't know that, here I am telling it to you now. So this is a math class. It's math for computer science, and it's going to be a lot of new stuff that you have not seen in a previous math class, okay? And we're going to apply it to computer science. So it's going to be, we're going to take some old stuff that we've learned before and study them in a lot more depth, okay, and be very precise about it. We're going to learn how to prove stuff, okay? So, yeah, this is probably the best description of the class. It's more tedious than it is difficult. You have to put in the time and do the work to learn all this brand new stuff, and eventually you'll get good at it, and it'll work out. So you just got to spend the time, all right? So just keep that in mind as you're going through the class. It's going to take some work. You're going to learn to write proofs, and proofs are in English. So you're going to have to learn how to write better if you're not good at writing. If you don't like writing essays, you might hate the proofs in this class, but it's just something you got to get good at, okay? I'm going to force you to do a lot of proofwriting. So there's that, and then this is the kind of the only computer science class at Clovis where like there's going to be written homeworks, and those are going to be a lot more important than the labs. It's going to be less programming, more math, okay, in this class, because it is a math class. So a lot of the homeworks that I give you are going to take up a lot of time. You're going to have to think about them, okay? But I promise, everything you learn in this class, you're going to see it again once you get to a four-year college. You are going to thank me then, okay? I can guarantee it. So this is a 4-unit class as well, so just make sure that you understand how your time is going to be spent. A 4-unit class means you're going to spend 4 hours like watching me demonstrate things. You're going to watch lectures. That's what 4 units means, right? 4 hours in class, and then you double that, and that tells you how much time you're going to spend outside of class each week doing assignments. So expect to get close to that rule, okay? This is a major level class. So with all that, I don't want to scare you away or anything. I just want to make sure you know what you're getting yourself into, okay? So I'll be here to help you as much as humanly possible, and so will your peers. So yeah, there's that. A few other things that I want to say. I'm just going to go lighting round through kind of the syllabus now. There's something called the Technology Loan Program through the school that will give you like a laptop to rent out for the semester, or even a hotspot router. Go and see our resources page on Canvas if you need to do that. This is an online class, so you are going to need a computer running Windows or Mac OS to take the tests in this class, okay? And you're going to need a webcam and a microphone. So just keep that in mind. Read more about this on the syllabus, but if you need something, like go to the library and they will give it to you if you don't have it already, okay? So just keep that in mind, and now I think it is time to go to the syllabus, okay? So you can get to it through our modules page or through this page. You do have to go to the modules page to unlock these, right? The only way that you're watching this lecture is that you've already done this, so technically I don't need to tell you, right? But I'm forcing you to look at all these pages. But here's the syllabus. Let's open it together. I don't want to open it. Oh man, can I open it in the browser? That works for me. Okay, cool. So, yeah, here's our syllabus. You can read it as much as you want, but I would recommend paying most attention to the exam section and then also the grading section, which is probably what you care most about. So here's what's going on in the class. You are going to be given written homeworks like math problems and then programming assignments, which I will call labs, pretty much every couple weeks. All right, you can expect to always have something to be working on. This is the one computer science class here where the homeworks are much, much more important than the labs. This is not a lot of programming, it's more math, okay? To make us better programmers still. There will be 2 midterms in the class, and this is like an 18-week class. There are like 17 weeks of lectures and then an 18th week of finals week. So I'll have the first midterm during week 6, which is like a third of the way through the class, and then week 12 will be the second midterm. It's like two-thirds of the way through the class, and then week 18, 3/3 of the way through the class is the final. Okay, so that's when your midterm exams will be. And then here's your grade breakdown. The written homeworks will be 25% of your grade, programming assignments on our class server, 15%, just reading your textbook and doing the assignments within that, 10%. 5% of your grade will be from the check-in surveys on Canvas. Those are fun. Please do them. And then 30% is from the midterm, so 15 per midterm, and then the final exam will be worth the same as a midterm. Why not? So that'll be worth another 15%. Okay, so yeah, that's your grade breakdown, and that's probably the thing you care the most about right now, probably. So okay, so there's that. What else do I want to tell you? So I will also be giving extra credit throughout this semester. One thing I do want to tell you straight away is there will be extra credit every time you go to an ACM Club workshop, where that workshop talks about something technical at least. No board game nights count for this, but I'll give you extra credit for going to any technical ACM Club workshop. So consider doing that. That more information about how to find those workshops is in our Discord. So there's a ACM Club Discord that you can go and follow and be a part of. and then I'm going to cap you off at 10% extra credit. Okay, so that's the maximum you can get throughout the semester is a letter grade's worth of extra credit. That is where I'll cut you off. So there's that. The check-in surveys, there is one out right now on our modules page. Please do it. Please do it every week. This is going to be how I take attendance in this class, first of all. Okay, so definitely do them, or first of all, you will lose points if you don't do them. And also, if you don't do the first one, I'm going to drop you from the class. This is going to be how I take attendance in the class since there is no actual lecture. So definitely do the check-in surveys. They're helpful for me. They're going to be just like me asking you questions and forcing you to like psychoanalyze yourself. So it's worth it. It's worth doing. It'll help you figure out like what you're struggling on and how to do better. And it will also tell me more about what you're struggling on and how you think you could do better as well. So it's a win-win. So there's that. And then, yeah, for the final exam, again, because this is not like a timed class, I have to give you a window to take it. So here's when we'll do the final exam. I will give you your final exam within a 24-hour period between the Monday and Tuesday of finals week. We're just going to get it over with. All right, so between the 19th and the 20th of May, I will give you your final exam. The exact time range to be determined, but I'll give you at least 24 hours to do it. All right, so that's when that's going to be. And I think that's probably what you wanted to know the most. This slide is probably the most important slide of this lecture, for you at least. So there's that. As far as the written homeworks go, I'm not going to grade you super harshly on them, I should say. Because it's just the homework. You're practicing something for the first time. The tests are where the stakes are high, right? So here's my promise to you. If you get at least 70%, if you get at least a C, right, of the questions correct, if you do your homework well enough to at least get 70%, and you made an effort on every part of every problem you tried, then I'll give you 100% on the homework, all right? It's meant for practice, so it's okay if you don't get everything, right? But you have to try on everything, all right? And get at least a C, let's say. If you don't get that, you probably should have asked a question, right? You should be asking me questions and coming to office hours if you're not understanding something. So that's my promise to you. And also just make sure that your handwriting is legible, because you're probably going to like, some of you will choose to like type up your homeworks, but a lot of us will do it on paper and just send in like a PDF of that. So just make sure that your handwriting is legible, because I will mark you wrong if I can't read your answer. So there's that. The next thing I want to talk about is due dates. I do something a little bit different to a lot of professors. I make all of my assignments in this class due at 5 p.m. on the day that they're due. So just keep that in mind. The due date, whatever it is, the assignment is due at 5 p.m. Okay, for every single assignment in this class, except for the check-in surveys, they'll be due at 5:30. This makes sure that I'm awake when things go wrong, because technical issues arise, right, with computer science classes. You've probably experienced that by now. So that's why I do it this way. Just keep that in mind. It's not midnight. Your assignments are all due at 5 p.m. Okay, I do make some exceptions for my working students. So if you work at least half time, if you work 20 hours or more per week, school does not count. Then I'll give you an extra 7 hours to do all of your assignments in this class. Then it really will be due at midnight for you, your stuff. Okay. If you work at least full time, or you do something that is the equivalent of a full-time job, like you care for a child, something like that, then talk to me. I will give you an extra 15 hours on your assignment. So you could either stay up late and wake up early and get stuff in. And I hope that we can all agree that the people that fall into these categories deserve that extra time, right? So let me know if any of those apply to you, and I'll get you in the right assignment due date group. Do keep in mind that these are extensions for just assignments, not for exams or anything like that, okay? So yeah, that's my due date policy. I also have a pretty lenient late submissions policy. I will accept a lot of things late, but I will take away half the credit the second something is late. So that's the give and take there, okay? So yeah, the one thing I want to say is that you need to tell me if you ever submit a textbook assignment late, because I have to go in manually into Canvas and change stuff. So that's that. And I don't accept late homeworks because I'll be giving you the answers. So that wouldn't be fair. Okay, so everything else though, I'll accept late submissions. I will also drop a lot of your lowest scores. So if you have a bad week, it's like nothing happened. Read more about that in the syllabus. And I'll be giving you, of course, all the stuff that I do in class on Canvas. You will see it. Okay. We are going to have a class server in this class, and hopefully you've experienced this by now, but all of your programming assignments, all of your labs will be turned in by some way getting them onto our class server. I would prefer it if you did all your work there, honestly. But I've made you all accounts, and hopefully you all have one. All right, so let me know if like something doesn't work, and I will fix it. Come to office hours if you're having trouble getting logged in, but hopefully you've done that already. All right, so that's going to be in this SSH client page, a video on how to connect. So also don't use some other program to connect without talking to me, because it will lock you out of your account. Okay, so that's a little bit about the class server. You'll learn more about it in the lab introduction video for the week. And yeah, we're almost to the end of all this logistical stuff. We're getting there. Let's next talk about our textbook. All right, so we're going to use a website called Zybooks to have our textbook. It is virtual, it's interactive. You sadly have to buy it because it's virtual and interactive. I promise it's worth it though. Like, it's going to have a bunch of cool diagrams, and it'll help you learn the material a lot better than just reading text. So you can get it in one of two ways. You can go to the bookstore or get it from the Zybooks website. If you can, please go to the website and get it, because I've heard horror stories that people go to the bookstore and like they have to be sent through the mail a code for the textbook, and that just takes a lot of time, and then you're behind. So please, if you can, get it from the Zybooks website. If you can't, no worries, I'll give you an extension, but just like keep that in mind. So the way that you get the book is, well, follow my instructions, but it's just going to be, you're going to go to the first link, like go to the first assignment in the textbook, like chapter 1. You'll click it, and it'll take you to the website and give you an option to buy the book if you haven't already. Once you've bought the book, it will take you to the actual chapter. So that's exciting, and like see how there's a bunch of cool diagrams and stuff, and like helpful things, right? It's not just a textbook where you're reading, you're interacting with it. So yeah, I've put all the assignments up. They're at the bottom. So if you have no life, here they all are. You can get started early on all of them. I've given like the right due dates because there is a certain order to these. We're going a little bit out of order. But yeah, that's pretty much the textbook. It's very, very cool. One thing I do want to tell you is to get to like the assignment instructions, it's kind of have to go out to the actual textbook's table of contents, and here are all the assignments. You can click on the one, and that will tell you like what's going on. All right, and you'll also be able to see how many points that you've got so far, and like this is where you go to see if it's working. All right, to see that you've done everything, and to know which sections I'm assigning per assignment. Okay, so yeah, just go out to the table of contents. It's in this assignments tab, and please pay no attention to these due dates. I have to make them the last day that things can be turned in so that you can get your late credit. The Canvas due dates are the real ones. Okay, so yeah, that's your Zybook, and it is beautiful. All right, it's going to be very, very useful. And this chapter 1 assignment means I want you to go through all of these sections essentially, and you can see your score. Okay, so that's Zybooks. We also have Discord for this class. I've made a Discord for all my classes, and it is wonderful. So please use that for discussion. So here, let me open it up. There's probably going to be some updates. It'll take a while, but this is how I want you to interact with me, please. So once you get to our Discord, it'll take you to the welcome channel. You want to scroll up to the tippy top and like click the 100 emoji, click the fox because you're in CSCI 26, click your pronouns, and then here is the ACM Discord, and this will be where the extra credit like workshops are going to be posted. So join that too, please. And yeah, that's pretty much it. That will unlock a lot of these channels like announcements in general. And CSCI 26 is the one where you can ask public questions to me and also to your peers. So yeah, please use that to ask questions. Ask questions publicly when you can so that your peers can help when it's 3 a.m. and I'm asleep. But what I don't want you to do is share a bunch of code or an entire answer publicly. So please, I trust you to use your judgment here, but don't like give away answers because that wouldn't be fair. So if you need to talk about like a ridiculous amount of code or like a complete answer, then I want you to send me a direct message instead, right? And so you can get to me by like right-clicking me and going to message. I can't message myself though, okay? So that's our Discord, very, very useful. And I highly encourage you to use that to talk to me, even through a direct message, instead of like through email or through Canvas, because you can imagine as a professor how disgusting my inbox is, and I might miss something from you. Whereas on Discord, it's very easy to see. I get a notification and can tell that I haven't read something. Okay, so there's that. next is office hours. Please come to office hours. You can come in person if you want, but every one of my office hours will also be available online. So my office hours schedule is up here. This may change after the recording, depending on like meetings that get assigned as the semester gets going. But here's kind of when I want to have my office hours. There we go. Got to zoom out. The green things, all right? These are my office hours, and you can click my office hours Zoom link either here or here to get there, all right, through Zoom. Or you can come in person. So yeah, that's when at least I want to have my office hours, but do check this. This might change. But please come to those whenever you need help. I'd be happy to help you. And yeah, speaking of help, we also have, first of all, the tutorial center is a great place. Please take advantage of that too, in addition to my office hours. And let's make a rule for ourselves, okay? You've taken a lot of computer science classes by now, so you know that like it takes a while for things to come to you. You have to like make a bunch of stuff churn together in your brain until things make sense, but you will eventually get stuck for a while. And if you've been stuck for too long, I want you to come to me or go to the tutorial center and ask for help. All right, so let's set a time. If you have been stuck for, let's say, 30 minutes on something and you have no clue where to go from there, then please come to me. Go to the tutorial center, come to office hours. I want to get you over that problem and on to the next problem, okay? That being said, though, 30 minutes is a decent amount of time, so expect to get stuck for like 29 minutes and then have a flash of genius, because that's kind of how computer science works, okay? So if you've been stuck for at least 30 minutes, though, please get help. There's no virtue in staring at your screen for 2 hours. I did that as an undergrad. It made my time not as fun, so I want you to do better, all right? So yeah, there's that. And then, yeah, we're almost done with the logistics. We're almost there, guys. So let's next talk about the class website. So that is lautensclass.com. So I've made you, first of all, 2 separate accounts. You hopefully have gotten in on the server already. That's the SSH client instructions. So you've got 2 accounts right now. You've got one in the class server, and the other is on our class website. That's in the web browser. That is lautensclass.com. All right, it's on this slide, www.lautensclass.com. It's wonderful. Here it is. Your username and your password are going to be the same right now, and I have made you the same account in both places, but they're 2 separate accounts. All right, that's what I want to say. If you change one account's password, like you probably have on the class server, your class website account is still the default one, okay? Your username is the same on both places, but you have 2 separate places to have a password, all right? Changing one does not change the other, but the account names are the same, all right? That's a little confusing, so I have a slide for that. So, but without further ado, our class website is lautensclass.com. Your username and the password, even if you changed it on the server, is your last name, all lowercase, an underscore, and then your student ID. Also get rid of any like hyphens or things. So like if this is my last name, this is my student ID, then this would be my username and my password for the class website right now. If this were my last name and this were my student ID, then this would be my username and my password for the class website. Okay? So hopefully it works for you. If I go to it and log in as my student test account, then this is what it looks like for you. You got all these pages, and probably the page you care most about is this AutoGrader grades page. Okay, so that's where we're going to be going a lot. The rest don't really apply to you because this is an online class. So yeah, this is the beautiful class website. It's going to be very helpful for checking your lab grades. So yeah, I think that's everything that I wanted to say. We finally made it through the logistics, guys. You did it. So pat yourself on the back, wake yourself back up, because now we can actually talk about CSCI 26. And I am very excited to get to this finally. All right, so let's figure out what is this class going to be about. So the technical title for this class is Discrete Mathematics for Computer Science. So what in the world is discrete math? Well, if you look it up somewhere, it's the study of mathematical structures that are countable or otherwise distinct and separable. So that's just me stealing words from the internet. What does that even mean, though? So in math so far, in your mathematical career, you've studied mostly continuous things. Like you've studied functions that look like this, right? That are wavy and have no like gaps between them. That's a continuous function, and that's like continuous mathematics, let's say. Discrete mathematics is when things are separable in some way. So like instead of making functions like this, discrete mathematicians are more like, all right, let's study this function as a bunch of chunks of values at a given time. like they're all separate. So that's kind of the difference between discrete and non-discrete mathematics. So we're doing this one. Trees, for example, something that you studied, are a discrete data structure. All right. So what that means is you can't have in between 2 and 3 nodes of a tree. You just have you either have 2 or you have 3. All right. So they're distinct. They're countable. That's kind of how discrete mathematics works. And here's a list of topics that you will see in this class. We'll talk about logic and use our logical knowledge to prove things with proofs. We'll learn like number theory, which is really cool, primes and stuff. We'll learn how to count things, because that's important. And then we'll learn probability theory, among other things. There's plenty of things to talk about. You'll learn about a data structure called a graph. So here's a picture of a new data structure that you'll learn in this class. It's called a graph. It looks a lot like a tree, but it's got less rules, right? There's no root or anything. You can have a bunch of, it's not even children anymore, it's like neighbors. So there's different terms involved. And yeah, that's what a graph is, for example. All right, that's something that you'll learn later and read about too. So that's discrete math in a nutshell. And now let me give you like a little sneak peek of some of these topics. All right, so let's talk about logic. Maybe you think you're already a logical thinker, but we need to go further. We need to get better at it. All right, so logic in general is the study of formal reasoning, and I will try to motivate to you why you should get better. All right, I'll prove to you that logical thinking is a very useful thing. All right, so here's a little exercise for you. Please, once I explain the question, try to pause the video and think about it yourself before I show you my answer. All right, it's very helpful to do it that way. So here's your question. What in the world does it mean for a vector to be sorted? All right, what is the definition of sortedness? Pretend that like I have amnesia and I know what vectors are, but I don't know. I've never heard the word sorted before, or I've forgotten. All right, how would you describe to somebody that this vector is sorted, but this one isn't? Okay, can you come up with a logical specification for what it means for a vector to be sorted? Do your best, give that a try, and then I'll show you my way of thinking. Okay. So first of all, I would draw out a bunch of examples. Like, okay, I want to be very precise, so let's make sure that all my words are going to be correct. So here's an example vector. What does it mean for a vector to be sorted? So like this vector, for example, is sorted, right? Sure. So that one's sorted, but like let's have an example of something that's not sorted as well, like so we can remind ourselves why this thing isn't sorted, right? 8, 6, that's supposed to be an 8. 7, 5, 20. This one isn't sorted, right? So what's the difference between the two? Like, all right, V1 is sorted because it's kind of like increasing, right? Maybe that's what you said. Maybe that is your definition of sortedness. And V2, it's not sorted because it's like it's zigzagging all around there, isn't it? But I think this is not quite precise enough. If you think about this longer, this kind of picture is not a good enough picture, all right? We haven't even gotten to English yet, but like we're not even ready for it. Because this is also a sorted vector, right? 1, 1, 2, 3. Do you see? See how this is not telling the full story there? So this is kind of what it means to be sorted. You can stay the same as long as you don't get any smaller. It's like a stair step. So that is a better idea. That's a better picture. And so we kind of have to turn that into words now and describe, like, what does it mean for a vector to be sorted? Let's come up with a logical specification. And so I'm going to write some words down that are going to be very mathematical, and you might not fully understand them yet. All right? You're going to get good at this kind of writing soon in the class. I don't expect you to fully understand what I'm about to write, though. Okay? But I'll do my best to explain it. So here is how we can specify in math with logical terms that something is sorted. All right? That a vector is sorted, for example. Let's say that we've got a vector. A good way to talk about how it's sorted and like things are increasing or staying the same is by using indices, right? Because you got indices at each element and they're getting bigger. We can say that, all right, look at all the indices, compare them, like in a certain order at least. Like, look at this index. It's less than or equal to all these guys. Look at this index. It's less than or equal to all these guys. Look at this index. It's less than or equal to just this guy, right? Because that's the end. And that's what it means to be sorted, right? We can put that into words. So how do we talk about like this guy and like everybody else? Well, we can just make up some indices. Like, all right, let I and j be indices. Be indices. This is mathematical speak right now. Let I and j be indices in the vector v we're trying to claim that's sorted. Okay? So like I and j, we want them to range like this. Like I can be here, and then j can be over here, or over here. It gets to like compare, right? I can be the first thing, and j can be the second thing. It's like in that order. It's like I could be over here, j could be over here. We want to try every possibility, essentially, of I and j, right? In that order. Would that make sense to you? Like, all right, let I and j range over all these possible pairs of indices. Let I and j be indices in V, whatever you want them to be, as long as I comes before j. Let I be less than j, all right? So it could look like this, could look like this, just j can't be on the other side. And here's what it means now, with that in mind, for a vector to be sorted. Let I and j be every possible one they could be, every possible pair of indices they could be. And here's what it means for a vector to be sorted. Your vector v is sorted if and only if, and there's a logical symbol for those words, if and only if it's true that v at I is less than or equal to v at j. For every possible value of I and j that works, such that I is less than j. That's what it means to be sorted. It's like try this out, and like try these out, and then even like I be here, j be here. It's like have them try every possible value, every possible combination of i's and j's that follows these rules. If you tried them all and this is true, the vector's sorted. All right? That's the secret. And like this one's not sorted because, for example, I and j could be this. This does not hold. You see that? But for every possible I and j, for this one and for this one, this is true. That's what it means to be sorted. That's one way to describe it, at least. And that's very precise and mathematical. Okay? So it's okay if that didn't make full enough sense to you right now. You're going to get better at this. All right? This is just your first taste of this. I haven't even taught it to you yet. All right? We're going to get there. So that's your motivation for logic and why you might want to get better at it. Let's talk about proofs as well. All right? So we want to be able to prove that our programs are correct. Right? That's very important for computer science. We want to know beyond a shadow of a doubt that what we're doing is right. Okay? So here's a simple example of that. Let me show you a simple proof. All right? So let's pretend that like this is our code we want to write. We want to sum the numbers from 1 to n, and let's say that this is our job so far. This is what we've done so far. For example, if n was 5, we would want to sum up all the values from 1 to 5. 1 plus 2 plus 3 plus 4 plus 5. Like that's the answer that we want. So we write this code. Hint, hint, there's something wrong with this code. Do you see it? We want to know for sure that the code that we wrote really does exactly this. Okay? So what you want to do then is you want to write a proof. Let's write a proof that guarantees that our code does the right thing. Okay? And so we want to know that by the time we get here, like, is it true that the sum variable holds the value of, like, for whatever n was, 1 plus 2, like that's what we want, right? 1 plus 2 plus 3 plus all the way to n. We want to prove that. Okay, and so we need some new terms. I'll teach you some new terms right now. To get there, we kind of want a post condition for all of this, essentially. So a precondition is a word that means it's a logical statement that's true before a statement gets executed. So a precondition is something that's true before code happens, and then a post condition, right, is something that's true after your code happens, after a statement of code gets executed. All right. So essentially, we want the post condition after all this code is done. What's true about it is sum holds this. Okay, that's what we would like to prove right now. And so, okay, here's kind of how you can think about this. Here's a statement. Nothing is true. Nothing has happened before it's run. But after this program, this statement is run, there's a post condition, right? What's true after this first statement is run? Int sum equals 0. Well, we've got a variable, and it sure better hold 0 right now. Does that make sense? Like that is true about this line, right? It's made a variable and sum holds 0 right now, for sure. That's a post condition of this instruction. And then, now it's time for this one. Do you see how the post condition kind of becomes the precondition for the second one? It's like, all right, what's true before this? What's its precondition? Well, all we know is that we're in a universe where sum is holding 0, okay? And so, all right, after this one's done, what's its post condition? Well, we know that sum is still 0. We haven't changed that. And now we made a variable called I that holds 1. Do you see how we're gaining logical knowledge after this program is getting run more and more? All right, so that's kind of what's happening there. And we want to essentially get a post condition down here for the whole program, right? We want this. But we're going to go through a loop, though. And we don't know how many times this loop is going to execute. It depends on n, right? So what we need for a loop to prove stuff about post conditions for a loop is we need an invariant. An invariant is something that doesn't change. It's something that's always true, no matter how many times you've run the loop. If you've run the loop not at all, or you've run the loop a certain number of times, one time, 2 times, 3 times, it never changes. It's still true, all right? So a loop invariant is just a statement that's true after any number of executions of your loop, for any k, after k executions for every k, after 0 executions, after 1, after 2, all right? Again, I don't expect you to understand what I'm saying right now. I'm just giving you a taste of all these words, okay? You will get good at this soon. So, all right, we need an invariant for this loop, something that's true no matter how many times we've run it. And here is the answer. Here is your loop invariant, all right? This is something that's always true no matter how many times this loop has been run, and we can prove that it is a correct invariant as well. So, all right, this is what's true, right, about this loop. Sum is always going to hold the sum of 1 plus 2 plus all the way to I minus 1. That's true before the loop even starts, all right? You need to check that. That's true, right? Because sum right now holds 0 once we haven't hit the loop yet, and that is correctly the sum of all the numbers up to I minus 1, 0 to 0, right? So that's correct. And we want to show that it still holds even if we ran the loop once, all right? So to prove it is like, all right, we're assuming this is true right now, right? Because it's invariant. It's true before. Let's ensure that it's true afterwards as well, all right? So, okay, let's say that we've hit our loop. I is less than n, like we run our loop some more. We know that this is true because it's an invariant. It's true before. We have to show that it's still true afterwards. So like, what happens? What in the world happens in this loop? We know this, right? We know that the sum is currently 1 plus 2. It's holding ... up to I minus 1. And then how do things change, all right? So, okay, the sum gets a new value in it. Sum gets I added into it. So like, it isn't sum anymore, it's like sum prime. Sum is changed into this. It holds what it used to hold, 1 plus 2 all the way to I minus 1. And we're also adding I into it, plus I. All right, plus I. And then I is also changing. I was I before, and now I prime, the new I, is whatever the old I plus 1 is. Okay, so these are like the new values we're getting. And we have to show that this invariant still holds, does it? All right, for these new values, for the primed things, like is it true that sum prime is equal to 1 plus 2 all the way to I minus 1 prime? I think it is, right? Because what is this, right? 1 plus 2 plus all the way, is this I minus 1? Yeah. Or sorry, I prime minus 1? Yes. Because that's the I plus 1 minus 1, that is I. Do you see that? It's a little complicated, but like it's working, right? That is correct right now. This is correctly I prime minus 1. It's like this invariant holds, and so no matter how many times you run this loop, this is true. All right? So that means it's true when we're done with the loop. All right? So what's true when we're done with this loop? All right? Well, if the loop ever stops, it means this condition is false, right? You've thought of this, right? You've considered this when you're programming before. So, all right, if this is false, what does that mean if I is increasing? Well, I must be, just due to the way that I is getting bigger, right? If I less than n becomes false eventually, that means that I got so big that it became n. Does that make sense? The only way that we got here, due to the way that I is changing, is that I is n now, all right? So we know that that's for sure true when this loop stops. And we also know, because of the invariant, what's true about sum. We know that the sum variable holds the value, the sum from 1 plus 2 plus all the way to I minus 1. But I holds n. That is n minus 1, right? That's the secret, right? Up all to n minus 1. Does that make sense? And that is what's wrong with this code. It's not correct, right? There was a problem. We wanted this all the way to n, but we proved that it's only going up to n minus 1. That is for sure true right now. All right, that's what we have at the end there. So you see what needs to change now, right? To get the proof to go through, beyond a shadow of a doubt, to prove once and for all that this works, you need an equal sign there too. So that will make sure that I ends, and it's not just n anymore, it's n plus 1, and that gives us plus n now, because that's I minus 1 is n. And that gives us our correct sum. And that is going to work for no matter the value of n. Isn't that beautiful? It's like, that's why you want to prove stuff about code. There's no need to write any tests. Like, you know for sure now this is true once you get all this proof stuff done. All right? That's very, very useful. All right? I hope you can see how this is going to make you a better computer scientist. Even if you're not going to write proofs all day long, you're just going to get the ideas in your brain to be like, all right, if I wanted to write a proof, here's how I can convince myself that this code is really going to work. All right, and that's going to make you really, really good. All right. So yeah, I think that's my short little introduction before we go to actual slides about normal stuff. The last thing I want to say in this just like first part of the lecture is I'm going to teach you a new language, because why not? I'm not going to force you to write it, but it's on the server. You can write it if you'd like. You can try out my programs, but you are required to write C++. I am not. So that's beautiful. And I'm going to teach you a new language called Racket. It's a functional language. It's a dialect of a language called Scheme, which is itself a dialect of an older language called Lisp. This is one of the very first languages that wasn't assembly. So it's beautiful. I want to teach it to you. All right? I'm not going to test you on it or anything. You're going to be forced to use C++ in your actual labs, but you're going to watch me write it, and your mind will expand because of it. Okay? So there is a tutorial on our optional reading page on it, but it's a very useful language. It looks very weird though. So like instead of calling functions like this in Racket, this is like C++ style. In Racket, you put the parentheses like this. You say the name of the function, and then the arguments go inside the parentheses as well. You just space separate them. So it looks like that. It's a little weird. And then it's just a bunch of parentheses all day long. As far as Racket is concerned, these are the same as these are the same as these. You can interchange them, but there are some conventions at least. But like, it's just it's a mess of parentheses, and it looks weird, and it's different. All right. So I'm going to show you that you can still understand it. All right. So let me show you a Hello World program in Racket right now. It's a brand new language to expand your mind. So here is a lecture 1 folder. So remember, you're going to get this code. And let me look and create a file called it's .rkt for Racket. Boop. And so to write a Racket program, first you need to say that let's not include anything, but it's lang Racket, because there's like sub languages. We want to use the full thing. And here is how you print Hello World. It's display ln, and then you put your string, Hello World. Right? So that's how a function call works. It's a little weird. And comments start with semicolons, which is also very weird. People, for some reason, they like to do 2 semicolons, even though you only need 1. So let me just write, the way to run this is through a program on the terminal called Racket. You say Racket, then you give the name of your file, hello.rkt. But people, they tend to use double semicolons for no good reason. So here, let's run it. Racket, hello.racket. Beautiful, right? So that's your first taste of the language. Let me show you a few more things, okay? Before we get to actual logic and normal stuff. So I pre-programmed this one. Here's a file called coolstuff.racket. Let me try to show you some more things. First of all, there's no main function. You just start writing code. It's kind of like Python. You've used Python before. Here's how you make variables. You say define, give the name, give the value. That's how you do it. You can make functions like this. It's like, all right, define a function called print from 1 to. You can have really cool characters in your functions too. You can have dashes. That's okay. Define a function called print from 1 to that takes a parameter n. And here's the if statement in Racket. It looks very weird, right? You say cond, and then just for ease of reading, you don't use parentheses anymore, even though you could have used parentheses here. You change up your parentheses, even though it doesn't really matter as far as Racket's concerned. It's like, all right, here's your first condition. If n is 1, so this is a recursive function, the base case, you want to print from 1 to 1, just print the 1, you're done. Otherwise, here are the 2 things you need to do. You need to recursively print from 1 to n minus 1, and here's how you do math in Racket. Everything looks like this, right? It's all like a function call where the name of the function is at the start. So it's minus n1, that's n minus 1. And then here I am printing n after that. So recursively print from 1 to n minus 1, then print your n. That's the recursive case. And so that's how you print from 1 to 5, for example, recursively at least. So cool stuff.racket. Isn't it beautiful? There it is, printing from 1 to 5. If you want to make structs, you do it like this. You say struct, the name of it, and the things inside. So a 2D point struct has two things, x and y, inside of it. And that actually makes some helper functions for you as well. It makes a way to get the x out, the y out, and to check if something is a 2D point. So here's how you can use that. All right, let's define a point, a 2D point holding 5 and 7. X is 5, 5 is 7. Y is 7. And then you can get the x part out using that helper getter that it makes for you. So get the x part of p, and here it is, printing the 5. All right. So there's that, and just a few more data types. lists, just like in Python, lists are like the major thing that Racket likes. And so here's how you make a list that holds 1, 2, 3 in that order. L1, you just say list. You could also, there's shorthand for this, you use a quote. List 1, 2, 3. So like everything is a list technically in Racket. So there it is, and it's printing 1, 2, 3. There's L1, printing it out. And then the cool thing about lists and functional languages called Racket is like functions are everywhere. You can pass functions to other functions as well. That's very, very cool. So like here's a function called map, and what it does is it takes a list as well as another function. So here's a function called add2 that adds 2 to its value that you give it, and you can map that over a list. So you map add2 over L1. L1 was this 1, 2, 3. It will create the list 3, 4, 5. Do you see how it's printing that right there? That's beautiful, isn't it? I love that. So that's very, very powerful and cool. That exists in C++ as well. It's just harder to get at. You can also make functions without names. This also exists in C++. So instead of just making a function that you're only going to use once, call it add2, and like have it pollute your namespace, you could instead just like say map over L1. Here's a function. Just give it inline. It's called lambda. You say lambda, the name of your parameter, and like what do you return? Give the body as well. So like you give the whole function, and it's called a lambda function. Okay, that's very cool. And so that's going to do the same exact thing. It's like you give the function on the fly. It maps it over the list. And another cool one is called filter. Filter extracts elements. It filters them out based on a predicate or a condition, essentially, a function that gives back true or false. Right? It extracts all elements of a list for which some function returns true. True in Racket is number sign t, by the way. So there's that. So this is filtering over L2, the list L2, which is what? That's still 1, 2, 3, right? Filter all the values for which this function returns true. It's like give all the values and compare, like is x greater than 1? See how it's weird like that? This is x greater than 1. It's going to filter out all the things in 1, 2, 3 that's greater than 1 and give that back as a list and print it. So that's just 2, 3. Isn't that cool? So that's Racket in a nutshell. You can also, there's a REPL, which stands for read, evaluate, print loop, and you can use it just like Python. Like here's how you do plus. It's plus 2, 2 rather than 2 plus 2. And you can give a bunch of things, 2, 2, 3, 4, stuff like that. And then it's Control D to exit, to get back to the outer world. So yeah, that's a new programming language in a nutshell. I'm not going to test you on it, but I'm going to show you examples from it. And it's very, very useful to poison your mind in a functional way. So yeah, I think that is all that I want to say for my little welcome mini lecture. That's just the first half of this normal lecture. So now we can actually learn logic. Like I've motivated everything. I've shown you all the stuff, and we're ready to go now. So I will see you in the next lecture video.